Hey everyone, welcome back to the channel. If it's your first time here, my name is Aiden Potts and we go through math and physics tutorials as well as how to improve the learning skills and mindset of a student. In this video, we'll be going over angle measurements in the form of radians. We'll be going over what a radian is, how to convert from radians to degrees and vice versa, and a couple example problems using radians. By the end of this video, you'll be able to understand what a radian is and how it's defined, be able to convert between angles and degrees, go over the unit circle in terms of radians, and special triangles in terms of radians. If you find this video helpful, please like this video and subscribe to the channel to see more videos just like this. At the end of this video, I'm going to be going over how to memorize more effectively. As humans, we evolved to remember spaces and places really well, so if we can leverage this technique, we can memorize things much more effectively. Alright, so before we go into what radians are, let's think about how we measure angles currently. Typically, we've been using degrees. We've been saying that things like a perpendicular line like this are 90 degrees. Maybe this is, 60 degrees. We have over here as a 180 degree angle. And finally, we have a 360 degree angle, or a full revolution. So this angle measurement of degrees is actually just a human construct. We decided a long time ago that a full revolution or a full circle is 360 degrees. Radians in some ways are actually a more reasonable way of expressing angles due to how they're defined. So what a radian actually is the angle such that the arc length, like this orange line, this arc length is equal to the radius. So in this circle here, we have a radius, and then we also have this arc length. And you can think of like the arc length, if you think of a piece of string, you could bend a piece of string into a curve, and then to measure the distance of that curve, you would straighten it out and measure from point to point. From here, what we're saying is, if this arc length is equal to the radius, so this r here, that means that the angle is equal to 1 radian. So now we have kind of a relationship between the radian as an angle measurement, the radius, as well as the arc length. So I'm going to say the arc length is s, and it is equal to the radius multiplied by theta. So now we have this arc length represented as a radius and an angle. Now, if I were to do the entire circle, or get the arc length of, starting from here all the way around, if I did that, then we could still say that the arc length is equal to the radius multiplied by this theta. And further, if we look at what I just did, the distance, or this arc length, is actually going to equal the circumference of this circle, because we went all the way around. And the circumference of a circle is just 2 pi r. So I can say that 2 pi r is equal to s in this case, and if we still use this relationship, we can say 2 pi r is equal to r multiplied by theta. Now, if I cancel the r's, because they're on both sides of the equation, we have that theta is equal to 2 pi. This means that the angle measurement in radians for 360 degrees, or a full revolution, is actually 2 pi radians. And as I said just previously, a full revolution is 360 degrees. So now we have 2 pi, because it represents a full revolution, is also equal to 360 degrees. And now if I, kind of divide by 2 and reduce this, it's going to be pi, or I'll say pi radians is equal to 180 degrees. Now if I use this equation, I can actually convert between radians and degrees. So if I wanted 1 radian, I could say 1 radian is equal to 180 degrees divided by pi. I could also do this the other way. So if I wanted 1 degree, I could say 1 degree is equal to pi divided by 180 degrees. Okay, so now I want to kind of use our knowledge of radians and our previous knowledge of the unit circle, which I did in the previous video. And I'm going to mark these kind of key points as degrees first. So 0 degrees, it's also 360 degrees, because if we go full revolution, that's going to be the same. Over here we have 90 degrees, if we have that angle there. And if I go a full angle like that, it'll be 180 degrees. Then below that, this will be 270 degrees, because it's 90 degrees past 180 degrees. And now, what I want to do is express kind of these key points, or these key axes, as radians. So what I'm going to do is, for 90 degrees, I'm going to say 90 degrees, I want that in radians. And so what we do is we look at our pi radians is equal to 180 degree conversion equation. And we can say, okay, well, if I want radians on the left side, or if I want radians of 90 degrees, what I'm going to do is I'm going to divide by 180 divided by pi. So I'm going to say 90 degrees divided by 180 degrees over pi. That will give me radians. So here, if I do 90, well, if I'm dividing by this, it's really just 90 divided by 180 multiplied, I'll do it in brackets, multiplied by pi. And if we reduce this down, 90 and 180, it's really just pi over 2. So we're going to get pi over 2 radians. And that is at this point here. So that is the angle from the x-axis to the y-axis is represented as 90 degrees or pi over 2. Now this can be done for all the other kind of axes. So for 180 degrees, that ends up being pi. And then for 270 degrees, that ends up being 3 pi over 2. And as we said previously, we can represent a full revolution or a full circle as 2 pi. Now we're going to go into the special triangles and express their angles instead of degrees as actually as radians. So here we have the special triangle, and again, if this isn't familiar to you, go back to the previous video that I made, and I went into how to derive this and how to kind of never forget it. So here we have the special triangle, the 30, 60, 90 triangle. We have side lengths 2, root 3, and 1. So the side lengths in radians is not going to change. It's just the angle that we're changing. Again, radians are just a different form of angle measurement. So here, if we have 60 degrees, and I want to get the radian version in this angle right here, so we're looking at 60 degrees, what I can do is I can say 60 degrees divided by 180 degrees multiplied by pi will give me radians. So if I do that, I can just reduce this fraction down, and I can say this is equal to, well, if I divide everything by 60, I'll get 1 on top divided by 3, and then multiplied by pi, I get pi over 3 radians. So I can put that angle here as pi over 3. Next, I'm going to do the same process, but for this 30 degree angle. So if I have 30 degrees, we'll do it in white, 30 degrees divided by 180 degrees multiplied by pi, that's equivalent of saying, okay, well, I'm going to divide the top and bottom by 30 degrees, so I'm going to get 1 over 30 degrees, this is going to be 6, and then multiply by pi, and that's going to equal pi over 6 radians. So I can write this 30 degree angle here in radians is pi over 6. And now we have our 30, 60, 90 triangle in terms of radians. So it's really our pi over 3, pi over 6, pi over 2 triangle, because this 90 degree here is pi over 2. Alright, so looking at our 45, 45 degree triangle, or I guess 45, 45, 90 degree triangle, we want to put this in terms of radians as well. So here, if I look at this 45 degrees, again I'm going to do 45 degrees, I'm going to divide this by 180 degrees, multiply it by pi, and that's going to give me pi over 4 radians. Now I can put this angle here as pi over 4, and over here, since it's the same as pi over 4, and of course this 90 degree angle is pi over 2. Alright, so now we're going to actually go into problems using our new angle measurement of radians, also using the special triangle and using the unit circle. So here, we're trying to find sine of 11 pi over 6. So first, since we're in radians, what I'm going to do is I'm going to mark down this is 0 pi. It's also 2 pi, because we go full revolution, it's the same angle, or same value, sorry. And then if we write up here, I can write 0.5 pi, because it's just pi over 2. So if I evaluate that fraction, it's going to be 0.5 as a decimal. Over here, it's going to be pi, so 1 pi. And then at this axis, or this negative y-axis, it's going to be 3 pi over 2. And I'm just going to write that as 1.5 pi. The reason I write them as decimals is when I'm looking at this angle, I want to see, okay, where would this lie? Is it bigger than 1.5 and less than 2 pi? Is it bigger than 0.5 and less than pi? I want to try to figure out which quadrant it's going to lie in. So 11 pi over 6, that's almost 2 pi. It's pi over 6 away from 2 pi. So I know that it's going to be in this quadrant right here. And I'll draw this kind of line in orange here, and I'm going to say that this angle right here is 11 pi over 6. Now if that's 11 pi over 6, I can write here as pi over 6. This would be negative because the sign convention for angles is counterclockwise, so if we're going this way, that would be positive, but if we're going this way, that's going to be negative. So we could write this as 11 pi over 6 in the positive direction, or negative pi over 6 in the negative direction. So now what I can do is I can use our new triangles that we have to find this value. So if I connect this to make it a right triangle, well, this is pi over 6, so I know that this over here, this angle is going to be pi over 3. So if we go back to our triangle, we can say, okay, well, pi over 6, if we're taking the sine of pi over 6, that's going to be opposite, so this 1, because it's opposite this angle, 1 over 2. So we can say that sine of 11 pi over 6 is equal to 1 over 2, but we have to account for if it's going to be positive or negative. So because we're moving in the negative direction, we're getting this side over here, which is in the negative y direction, we have to put a negative 1 in front of that. And that would be our answer, negative 1/2. So looking at this example, we have cos of 5 pi over 4. So that's exactly pi over 4 greater than pi. So we know that it's going to be in this quadrant here, looking at kind of our numbers here for each of the axes. So what we're going to do is we're going to draw this as a right angle triangle. And now if we look at our special triangle, we know that pi over 4, well, if we do cos of pi over 4, that's going to be 1 over root 2. So we're going to say cos of pi over 4, which is the same as 5 pi over 4, is going to equal 1 over root 2, but we have to see if it's negative. So we're doing cos, and we're going, well, cos is the x direction. So are we going in the negative x direction or positive x direction? Well, clearly, this is the negative x direction, so cos is going to be negative right there. So again, we have cos of 5 pi over 4 is equal to negative 1 over root 2. This also, goes in line with the cast rule, if you prefer that method. Obviously, if we're in this third quadrant here, the only angle that's going to be positive here is a tan, because it's going to be sine over cos, and both sine and cos are negative, so two negatives, or a negative divided by a negative, is going to be a positive. So you can either go with the cast rule, like an acronym, and remember it that way, or you can just remember that if we derive the unit circle, the x direction is going to be evaluated as cos of x, and the y direction is going to be evaluated as sine of x. So here we're going in the negative x direction, so the cos is going to be negative. Okay, so now we're moving on to another example, that's tan of 4 pi over 3. So here, again, if I rewrite our 0 pi, 0.5 pi, pi, and 1.5 pi as our axes, we can see that 4 pi over 3, well, it's just pi over 3 bigger than pi, so this in here is going to be pi over 3. If we draw that out, we can now draw our pi over 3, pi over 6 triangle. So this is going to be root 3, this is 2, this is 1, this is pi over 3, and pi over 6. So if we look at that and we look at pi over 3, well, what we're going to get is tan of 4 pi over 3. That's going to be the opposite over the adjacent because of SOHCAHTOA. So tan of 4 pi over 3 is equal to, and we're going to get root 3, because that's the opposite angle, over 1. Now we need to check if it's positive or negative. So the opposite side, that's representing the negative y direction. So that's going to be negative right there. And we're going in the negative x direction. And that's the adjacent side. That's going to be negative 1. So if we evaluate this expression, negative root 3 over negative 1 is just going to be positive. So it's going to be tan of 4 pi over 3 is equal to root 3 over 1. And again, that makes sense if we do it the acronym way, because tan is positive in this quadrant, and because the angle falls in this quadrant, that means that it's going to be positive. Alright, so now I want to go over some of the kind of special angles that we can evaluate without even using special triangles and just knowing our knowledge of the unit circle and what it actually represents. So here, if it says sine of pi over 2, well, I just know that pi over 2 is a 90-degree angle, right? It represents from the x-axis to the y-axis. And I also know that on the unit circle, sine is corresponding to the y value. So here, we actually have a value that is completely in the y direction. It's not in the x, or the positive x, or the negative x. So I just know that sine of pi over 2, if I were to look at the unit circle and evaluate it, that's just going to equal 1. Because our hypotenuse is in the y direction. It's only in the y direction. So that means that our sine of pi over 2 is going to equal 1. Now if we look at cos of 2 pi, well, cos of 2 pi, that's like this entire angle here, and it's going to be along this axis. And based on the unit circle, I know that cos of an angle, that's really just the x-coordinate. This line here only falls on the x-axis. So I know that cos of 2 pi is also going to equal 1 because it does not lie in any direction in the y direction. It's only in the x direction. So that unit circle derivation again, we're going to see that if it's only in the x direction, that's the hypotenuse, so it's going to be 1. And just to hammer this point home, if I were to do cos of pi over 2, well, we already know that it's that orange line there. And we already said that it actually doesn't exist in the x direction at all. It's only in the y direction. So cos of pi over 2 is actually 0. And in the same format, if I do sine of 2 pi, what that actually is saying is sine of the angle that's horizontal. But sine is representing the y-coordinate, or the vertical direction. So again, sine of 2 pi is just like cos of pi over 2. It's going to be equal to 0. These values here are extremely important to move forward because these are what actually evaluate the trigonometric function. So like y is equal to sine x or y is equal to cos x. If you can remember and understand the unit circle, you can always remember how sine and cos behave because of cos representing the x direction and sine representing the y direction. Alright, so I want to talk now about how to memorize more effectively. And typically I'm not really a big proponent or advocate of memorizing because I really think you should understand the concepts, and if you can derive them, especially in math and physics, it's kind of more permanent in your memory. You're not really memorizing facts or memorizing formulas, you're understanding how they work and proving it to yourself each time. Having said that, there are some aspects where memorization is extremely important, and I want to kind of explain to you the most effective ways to memorize. So I think many people assume that they either have a good memory or a bad one. And what I'm going to say to you is kind of typical what I usually say on this channel is that that's not true, and these things can be developed. Some of the world-class memorization champions talk about how they developed this skill, and they weren't good at it initially, but over time and practice, they've actually now become world-class at it. Additionally, they're not just special cases. They think that anyone can memorize these or use these techniques to become better at memorizing. What's common among these memorization champions is they use this thing called a memory palace. And what a memory palace is taking a familiar environment for you, so it could be your school, your house, or the town you grew up in, or something like that. And what you do is you take pieces of what you're trying to memorize and place them in different locations in that environment. So say it's like a speech you're trying to memorize. And what you could do is, when you're walking through this environment, you could put it in order of how your speech is laid out. So you could walk into your first room of your house and have the first part of your speech in one of the corners of the room. Next, you go to the next part of the speech, and you have these as images in each corner of the room until you move on to the next room and go through that process again. Now, when you're walking through your speech, you actually don't need to really memorize each of the parts and how they kind of relate. You can just walk through your house and look at each individual section and memorize it that way. The reason this is so effective is because we're actually capitalizing or leveraging how our brains are actually wired. As humans, we're amazing at actually remembering and recalling where things are in space. This spatial recollection, or I guess spatial awareness, served an extremely important purpose from an evolutionary perspective. Thousands of years ago, we needed to know where water sources were. We needed to know where edible plants were, and most importantly, where dangerous animals' territory were so we could avoid it. So when trying to memorize for school or for work, try and use this technique. Place objects, or the things you're trying to memorize, in certain sections of a familiar environment that you have. Next, when it's time to perform or recite what you know, what you can do is just walk through that environment and pick out where you placed each object and in which room it was in. Thank you for taking the time to watch this video. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. I make a ton of content to help in math and physics, as well as improve the learning skills and learning mindset of a student. If you have a specific topic you want me to cover, let me know in the comments down below. Thanks again, and I'll see you guys in the next video.